I work at AP Plus Rescall, and I am the project coordinator for the Tempest project. Unfortunately, I can't share a whole lot of results with you because we started in May of last year, and so we have yet to get to the point where we have validated results for public dissemination, but we will have some probably beginning of next year once we get past the RP1 meeting. But at the very least, I can introduce you to the Tempest project and talk a little bit about our goals and objectives. So the Tempest project is focused on developing and maturing safe by design, high performance and lightweight batteries, but which are most importantly also recyclable. So we want to address the challenges of basically right now, a lot of batteries, when they reach end of life, you run into, as all of us know, the issues of critical raw materials and handling the waste. In addition, the metal housings right now also add a lot of weight. And so one of the primary things we'll also be dealing with is implementing composite housings that are designed to be safe. So this can basically be broken down into 5 separate objectives. The first one is to focus on next generation cell technologies. So these will be both classical lithium ion, and also solid state batteries. And both of these will be integrated into new architectures that integrate technologies for improved safety, thermal management, and performance. And at end of life, these battery designs will also have methods for improved recycling. And this is not just a matter of integrating methods for clean separation, but also recycling of whatever is left over in the black mass at the end of life. And then finally, we'll also develop new models for the optimization of batteries, and we will develop sustainable value chains and exploitation strategies, especially focused on what we call energy storage as a service models. So overall, we can boil this down into 4 primary impacts. There's a lot of other KPIs, but the most important ones that come out of this is that we want to achieve batteries with an overall recyclability of at least 70% improvement. We want to improve the optimization of the costs and the manufacturing effort by 30%. We want to improve the battery performance by 15% and the weight by at least 15%. The end result is that we project a reduction in the greenhouse and aerosol production by 62%, reduction of energy loss, and increase of range by up to 52%. And the end result is that then, depending on the application, for example, if you propagate this over into aerospace, use in aircraft, for example, you can remove essentially up to 78 tons of CO2 per battery pack per year. You can reduce the energy loss and increase range of up to 57% in rail applications. And if you talk about energy storage applications, you can reduce the overall energy load of the grid by up to 72%. And these are all preliminary figures from our ongoing life cycle and costing analysis. Now, the technologies in Tempest project basically fall into 3 specific groups. In performance, we are looking at moving directly to cell-to-pack architectures. So we do that obviously to improve the gravimetric and volumetric density of the systems. We are also developing optimized BMS systems. And both cell chemistries are that we use in the Tempest project are being improved to basically improve energy density. And we will also be integrating in lightweight innovative thermal control systems. And this functions on two levels. It functions at the level of cooling, so to most efficiently evacuate heat, but it also we also have methods to preheat the cells and to maintain their temperature at low operating temperatures, or in the case of solid state cells, to maintain them at an optimal operating temperature. So we have technologies both to heat and cool them. From a safety standpoint, since we are working with composite housings, although the principle of crack detection applies equally to metal. In the composite housings, we are integrating in a guided wave structural health monitoring system to detect in near real time defects as they arise, so that, for example, due to an impact on the undercarriage of the battery in a car, a driver can be warned that they need to take it in for service as soon as possible. In addition, the battery housings will include coatings for both flame retardant and resistant materials. So on the outside, we'll have essentially flame resistant coatings to protect them in the case of any external heat sources. And on the inside, we will include coatings for auto extinction of cell fires. In addition, as I mentioned before, we'll have thermal management techniques to eliminate heat, and the bottom of the exterior housing of the packs will also include impact-resistant coatings. And finally, from a sustainability standpoint, the packs will include one of Rescol's technologies for debonding on command, such that the packs, when they're assembled, will be very easy to assemble and will, maintain their structural integrity throughout their lifetime. But at end of life, it will be very easy to trigger the disassembly and essentially separate them into their component parts, either for reuse, recycling, or some other end-of-life treatment. For the black mass materials, that is to say the metals and or graphite, we are working on methods for hydrogen-based methods for cleanly extracting, recovering, and transforming the components of the cells. And then we are also working on digital tools to improve the overall performance of the cells. And so this basically boils down into, as I said, 5 different approaches. There's the demonstrators. So we will establish the specifications and circularity models that we've already done. The cell pack design and optimization. We have already done all of the cell and pack design. We've done the first stage of optimization, and we are just beginning to work into the part of materials modeling, testing, and manufacturing, stages 3 and 4. And 5 is also underway. But what I want to point out is that stage 2, this part of cell pack design and optimization, is an ongoing process, and based upon the results that we receive from 3, 4, and 5, that will automatically feed back. And just prior to the work, because we have a total of 3 more meetings coming up. We have the meeting at M18, M26, and M36, the end of the project. At M26, it is our basically pre-demonstrator manufacturing review meeting. And it's at this point that we will do another review of the results of all of this and basically do a retweaking, reoptimization of the cell design or the pack design. And so the consortium includes AP plus Rescol, Fraunhofer ICT, ABEE, the University of Patras, the National Institutes of Chemistry in Slovenia, KTU, Techniker, Sustainable Innovations, University of Bath, and the Institute of Advanced Automotive Propulsion Systems. And just one final thing, this is the contact, but one final thing I want to point out is I am also the chair of the EU Ingenious Battery Cluster. And the battery cluster includes the 5 projects that were funded under the same call as Tempest. So this includes BATS, Extended, VersaPrint, and NextBat, in addition to Tempest. And so we will all of us will be present at Battery Innovation Days. So if you have questions for me or any of the other projects, if you want to see us, we will be there.
Chi sta prendendo?